I'm going to start this video with some stuff already written down because I wrote it all out and it was in the middle of this video and got interrupted. So I don't really want to sit here and rewrite all this again, but basically we're doing our introduction to power generation, and so I'm talking a little bit about different energy sources that we can have. The first type of energy source we have to worry about is called a primary source. These are sources that are just found in nature, and then I listed some of them. It's coal, oil, wood, gas, food. That's just for us eating food. And other animals, uranium, the sun, wind, which is kind of the part of the sun since the sun causes that one, tides, which is a little bit from the sun because the sun does cause some tides, but mostly that's from the moon. Mountain lakes where we'd find water up high, which I think again attributes back to the sun for evaporating that water and moving it up to the top of that mountain. Rivers, flowing rivers, which is water flowing down usually from higher places like mountain lakes and such, which again I think goes back to the sun. And then geothermal. Yeah, that one's kind of hard to read, but I did write the word geothermal there. And so you need to know these things. I think you could also probably add to this list would be magnetic fields. They would be a part of that. And I can't do anything. Okay, sorry. Wasn't able to write there. Then we have secondary sources, and these are basically created from primary sources. It's what you get from them. So you could burn coal or oil or use the energy inside rivers and stuff to generate electricity. This is mostly what we do, but we can also use heat. This could be like an old school an old school engine for like running a train or something. You would burn coal in it and produce heat that would then be your source of energy for moving your train down the track. So there's that. And then we need a couple ways to actually compare these things. And mostly we want to compare the physical ones, so not really the sun or anything like that, but the coal, the oil, the wood, these kind of things. We want to compare them, even food. Then we can come up with a couple terms that go along with that. So the physical fuels, we want to compare which is the best, which do we get our most bang for our buck, so to speak. And so the way we talk about this is we need two terms. One is specific energy. You should know that word specific by now. Whenever you see that, that means it's going to be something per mass. And so specific energy would be energy released when you're using that per mass. So you want to look at something like this where, say, you burn a piece of food and you measure how much heat comes off it by seeing how much it heated some certain known amount of water up, because you know the heat capacity of water, and so you heat up the water and you see how much energy was actually released while you burned that fuel. And then you could figure out what the energy per unit mass is, and of course if it's a per unit mass, it's a joule per kilogram. All right, a joule per kilogram there, and the energy released per mass. So anytime you see that specific, remember it's a per mass. And then we'll have an energy density. So energy density, we see this word density, and unless they put the word like linear or something like that in front of it, then this is a per volume thing. So this is energy released per volume. And so using these two things, we can kind of compare how good each of these fuel sources are. And of course, this would be a joule per cubic meter, so, an energy per volume, as this was an energy per mass. And so these are our two basic terms we would talk and discuss these things in. So you could look at something like like a donut, and a donut's specific energy is just going to be much, much, much lower than that of coal would be. Burning coal would give you a lot more energy per volume and per amount of mass that you would have. Okay. The other way to talk about this kind of stuff is through Sankey diagrams. And I'll do another one of these later in the next video because it'll go along with what I'm talking about. And it's always good to see a lot of these. So a Sankey diagram, and basically you're going to have three little rules for this. One, they must be drawn to scale. That's important for when you draw them because you have to be able to use these to get information from them. How much energy went in and how much energy went out and how much energy went where, just by actually looking at what it is, how to scale it is drawn and reading it off the axes or something like that when dealing with this. Two, the way we're going to draw them, and you can look up on Google and see a lot of different ways where this is done, but the way I'm going to typically draw them is that wasted, I want to put that in quotes, wasted energy, because it's wasted only if you don't have a use for it, I guess. Was wasted for one thing isn't necessarily wasted for another. So wasted energy is either going to point up or down. Wasted energy goes up or down. And I'll show you that. This will make a little more sense when we draw one here in a minute. And then the third thing you need to keep in mind is then the last part is the useful energy. The energy we can do something with goes out the right side. Okay? And so if we go to draw one like this, we could say, let's say we had, I don't know, let's say 20 joules of energy being produced. So we would look at this and we'd say, all right, here we have 20 joules of energy going in. So this left-hand side, this would be where our energy comes in. This is what we're starting with. This really should have been a straighter line than that, sorry. So we have 20 joules coming in, and then after that we're going to look and see where does it all go, how is it distributed, and so anything that's lost, we would say along the way, like we'd have a little arrow or something that pointed down here, and then you could label also what the energy was lost to, and so we could say we lost 10 joules of energy here, and this could be something specific, a specific kind of wasted energy like through black body radiation, or it's wasted through heat or something like that. So we'd have 10 joules, say, coming out here, and that would cut our total energy in half. So this would need to be a scale that I would then reduce that, because I had 20, but after this is lost, I only have 10 left, right? So if this is 20 here, this would have to be then 10, and if we had a scale over here on the side, like an axis, we'd have to be able to read 20 here and 10 there. Okay, so you may be required to do something like that. And keep in mind you read it between the arrows. And the same thing with this. This width here, I didn't do it very well, should be the same width as that. They should be to scale. Okay, so this here should be the same as that there, where they're both now 10 joules. So we're down to 10 joules of energy, and then you could come over and say you had 4 joules of energy lost. And again, it's based on the width of this part, not the width of the arrowhead. I've had students in the past measure it on the arrowhead width and not the width of the actual, more like the shaft of the arrowhead. And so we could have, say, another 4 joules coming out here, and that 4 joules would drop us down to having only 6 left. And then you could come over and say have like 1 more little joule of energy being wasted here, 1 joule wasted here, and that would bring this up, and we'd have just our last little bit here. And so coming out and being useful, then we'd have just our 5 joules that we got from this, and we would then be able to tell tell how efficient this was. So you should be able to come along and measure this width here and compare it to this width here and say, all right, well, I'm looking at this, and this here tells me that I have 5 joules left, because I'd measure it back over and look on my vertical axis here. And so then you could do efficiency from this and get that our efficiency would be 5 joules over the 20 joules that we had initially, and that would be 25% efficient. So something like that. When you see real ones of these things would be labeled, like it'd be labeled with what kind of waste heat it was and what kind of energy was coming out and what kind of energy we'd be putting in. But this would be your basic idea. Sometimes the arrows could be pointed up, sometimes there's up arrows and down arrows. and sometimes they don't even really leave. Sometimes they just all go over here to the right. It just really depends. But the main basic thing, uh, I guess I put 3 rules here for how we're going to do them and how you'd be expected to do them in this class. But the main basic thing is this: draw it to scale. Okay, draw it to scale and label everything. All right. Well, you basically really want to do that. Make sure it goes drawn to scale because you want to be able to get quantitative data from this. You want to be able to just grab this out and measure the scale of these things. So even if this wasn't labeled as 10 joules, I should be able to measure the width of this, see it's half the width of this or the height of this, and know that 10 joules was out. So you need to be able to get that quantitative data from this as well as the qualitative data about where everything is going. All right, that's pretty much everything for the introduction.